Here is Bendy problem number 3. See if you can see what's different here. It's the same kind of problem that we've been working on, but there's one additional layer of complexity, and that is the surface that number 1 is going to be sliding on isn't completely flat as in Bendy problem number 1, and it isn't completely straight down as in Bendy problem number 2. It's in between. So this incorporates motion on an inclined plane into these bendy connected body problems. But you'll see it's not a big deal. It's just one little additional step to think about as we solve the problem. So in this one, we're going to do the same thing as we did before. We're going to determine the acceleration of, you could either call it number 1, we could determine the acceleration number 2, or we could determine the acceleration of number 1, rather, number 2, or just the system, because it's all going to be the same. Remember, that's one of the key points in these solutions, is that whatever 1 is doing in terms of acceleration is going to equal the acceleration of number 2, and it's just going to be the acceleration of our system. So this is the one that we're really going to be after. As before, our magic pulley has the attributes of no mass. That'll make more sense when we get into chapter 7, and then it also has no friction. So all it does is bend what's going on. It has no influence on the acceleration other than to cause the change in direction. Okay, let's get started. The first thing I want to think about in this case, and actually in the other cases, is what force would tend to make M1 slide down the block, and what force would tend to make M2 fall down this way? And those are both going to be gravity forces. Let's do the easy one first, because we know about the gravity force on number 2 is simply going to be just M2 times G. Now M1, we have to think back, what did we learn about motion on inclined planes? Basically, I don't want to redo the whole thing because that'll just take too long and you'll... Don't meander, McIntyre. Stay focused. Okay. All right. So we learned that basically, even though gravity is straight down, we're only going to... It's only the x component. What color do I want? It's only the x component. Remember, we're on ramps, inclined planes. We orient the x dimension parallel to the ramp, and the y dimension is perpendicular. So I'm doing too many colors here, but this is Wx. This component of gravity is what's going to tend to make 1 accelerate down the ramp. The y component, which is straight in, isn't going to tend to cause any acceleration. Okay, so how do we get the x component of gravity when something's on a ramp? Well, let me just write it, because and then we can review it if need be. Okay, so Wx is going to equal mg sine, okay, I'm going to say theta, and then I'm just going to go ahead and say, let's not call that alpha, let's call that theta. And okay, so how do we get the acceleration down the ramp? We're not going to do any numbers. We're not even going to do numbers on this problem because we don't need to. I was just thinking, I don't have the angle, I don't have the masses. That's okay, because putting in the numbers is the last step, and it's fairly trivial. All right, so let's straighten our problem as before. All we need is the magnitude of the acceleration. I already know the direction. And okay, for now, I'm assuming that 1 is way more massive than number 2. That's just an assumption. It could turn out that it won't be correct, and we'll talk about that briefly here. So here's number 1 in our straightened problem. Number 2. Okay, so here we are. We're basically determining acceleration of the system of 2 or 1. It doesn't matter. All right, let's put in those forces that are going to tend to cause acceleration. To the right, quote unquote, in my Bendy problem, I've got M2G. I also need a frame of reference because I need which way is positive, which way is negative. That kind of applies to this. All right, now what's going on here? To the left, or down the ramp, is going to be, well, I'm going to assume for now it's a bigger force. M, oh, that should be a 1 in there, m1g sine theta. Okay. The next thing we want to do is set up Newton's second law. So the acceleration of object 1 is going to be equal to the acceleration of the system, which in turn, we just need to add up the forces on the system. In other words, we're not going to think about tension in the string yet. Okay, then I divide that by the total mass of the system. Okay, now for the net force, I just put in my two forces that would tend to cause this thing to accelerate. In the positive direction, I have the weight of object number 2. So that's positive, m2g. That's this guy right here. It would tend to cause this little bucket number 2 to come down this way. But there's another force that's going to tend to want to make it go down the ramp, and that's our m1g sine theta. And that's negative because it's in our straightened problem, it's going to the left, and in this problem, the real problem, it's going down the ramp. So that's m1g sine theta. And the total mass is going to be m1 plus m2. And there is the answer. Now you say, well, which direction is it going to accelerate? And, well, if this ends up being positive, so if we take the gravity force on number 2 and subtract the x component of gravity on 1, and we get a positive number, that means it's going to go this way. But suppose that number 2 was actually quite massive and number 1 was kind of wimpy. Then, no, wait a second. Oh, shoot, I got to backtrack it. Boop. Pay no attention to what I just said. Okay, I had it backwards. Okay, so if this ends up being negative, sorry about that. If this ends up being negative, then that means it's going to go down the ramp. Because if this guy, which is the x component of gravity, is bigger than the gravity force on number 2, then it's going to go this way, which is negative, and for the real problem, that means it would go down the ramp. Okay, so, but it's possible, if 2 was bigger and 1 was smaller, it's possible that this, the gravity force on the bucket, could be greater than the x component of the gravity force on the block. So if this were to become a positive number, this minus this is positive, then it's going to go this way. So actually, I'll just say that if it turns out A1 equals negative, then block number 1 goes down the ramp. And if A, I should put if A1 comes out to be a positive value, then block number 1 slides up the ramp. Okay, this video is getting kind of long, so I'm not going to talk about the tension, but you would do exactly the same thing that we've done in all these problems. Is you would think about what is the force required to make number 1 accelerate at a certain rate. Anyway, it's exactly the same as the other problems. Okay, there you go. That's Bendy problem number 3.